Hello viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about a very requested topic, dark matter and dark energy. So let's dive right into it. Well, first we have to understand what was the problem with our current understanding of the universe that we had to introduce dark energy, dark matter and all that jazz. So you have to understand this. Universe does not make sense. Flat out, it does not make sense. So you might be like, okay, that means our understanding is wrong. Now that's the problem. Our understanding of our current universe is so good that we can launch Voyager. Now, why Voyager is such an interesting thing? Well, think of it this way. We calculated paths of a planet years in advance, multiple planets in. It's not like, okay, from Earth to Mars. It's like Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. We've calculated almost all the gas giants and we got there. It's like we launched for it and we reached it. Imagine that. Like in vast emptiness of a space, our calculations are so precise that a tiny spacecraft can fine-tunely hit something that is moving at a like planetary speeds. Like we did that. Like our mathematics is correct. Otherwise, we would not be able to do that. Like our mathematics is so correct that we can calculate how much time moves forward in our GPS satellites. It happens. It's a real. It's known. It's calculated. Like that's how accurate our mathematics are. So how the heck these two things can happen in the same time? It's like we are trying to understand the universe, and on a local scale everything works well. Like we got this, like we are king of the hill. But the moment we go to universe scale or even galaxy, it's like, bro, what the hell? Does not make sense. So what does that mean? That inherently means our mathematics is not wrong, it's incomplete. Basically we are missing certain variables, if you will. So that's the problem. It's not as cut and dry as like, oh, we are wrong. No. Again, we know things. We absolutely, undeniably can guess things. Our mathematics does work. So throwing away the mathematics right now would be like, yeah, you will end up creating the same thing. Why? Because it's absolute, it's known, it's tested. And science only accepts one thing: predictions. Like, can you predict reliably enough, accurately enough, within the margin of error? If the answer is yes, only then people move forward. So we know for a fact that our known science is not gibberish. It's absolute. So what the hell happened? Well, we can see some effects that are not matching with our current Newtonian physics. Let's just say that classical physics is just not matching up with that, but we cannot affect the cause of it. So what does that mean? That simply means there is a beach and you are seeing the footprint, but you are not seeing the person who is living the footprint. So that's the problem. That's why we had to introduce such a magical term in science, or like dark energy and dark magic. We might as well be calling it magic. It would not make any difference. So first thing, the first evidence that we got our mathematics is ludicrously wrong or incomplete is that galaxies spin. Now, like, okay, galaxies are there, they spin. What's so funny about that? Well, there is not enough matter in galaxy to spin at the current speed. So let's say our current galaxy RPM is, let's say, 1 RPM. With our mass is m. Here's the no mathematics allows that to be possible. It's like our m has to be either too high or RPM has to be too low. So how the heck it's happening? It's basically the spinning speed of all galaxies that we are observing. It's not that we observed one galaxy, it's like multiple of them. It's like all of them is too fast. So what will happen if you are too light and you're spinning too fast? You will spread apart, like you're gonna scatter everywhere. So you will not have formation of galaxies as we have right now. So flat out our Newtonian physics is like not holding together properly, and that's the problem. It's like something is adding gravity or something is reacting in such a way that it's doing something to the gravitational constant, and it's like, yeah, I'm making you more massive than that. So something on a large scale is doing something like this, and that's why we can see galaxies. Now you might be like, okay, is it limited to galaxies? No, it extends afterwards. Like in small scale, basically like a solar system, it does not matter too much, but the moment you start to go outwards like galaxies, it's like, whoa, completely math starts to drift off. And then you go to supercluster where you have millions and billions of galaxies, and then it's like completely different ballgame. So something is adding gravity, otherwise like the things should have fall apart, but it's not. So something is adding mass to it. How the heck, we have no idea. And the bigger our scale of the universe becomes, the more it's like, yeah, our mathematics is starting to drift much more. It's like on small scale we got this, we good, but the moment you galaxies, superclusters, yeah, forget about it. It does not make sense. So and what we have here is basically something that is not interacting with anything. Now you might be like, okay, how would you see something that is not glowing? We have more than enough method to see things that are not glowing. We can see dust cloud on another planet right now. So we got that. Like we can see things that are basically not glowing, basically non-luminous as we classify it. But somehow we can't observe this because it's not reacting to anything, including itself. So we call this dark matter. Now, dark simply, the scientist who coined the term dark matter for this, so dark simply means we do not know. The dark is that unknown factor, and matter, because in early mathematics it appeared just as like a matter, so they're like, yeah, just put it as a placeholder. But I like Neil deGrasse Tyson's on that. Is like they should call it YOLO and YOLO, or like Farad and Velma. Basically, it does not matter. We flat out do not know. It's just unknown. Basically, how we do in mathematics, like find x or y, it's like find x and y and all that jazz. It's the same thing. We know something is there, absolute certainty. Now, like how the heck you can know something is there? Well, we have telescopes. We can observe its effect, because we know for a fact that our mathematics is right. We know for a fact that galaxies are spinning, so we can calculate invert. It's like, okay, we have this, we know the known mass is this much, spin is this much, how much we have to add, basically how much x we have to add in order to balance the equation. So that will tell us how much dark matter is there. Now, the further we realize something, it's dilute, and that's why we flat out remove, oh, there are black holes without the excretion disk. No, it is ludicrously dilute. It's so dilute that in this volume, basically, where you're seeing my arms flying around, it could be hundreds of particles moving around. Now you're like, isn't that a lot? No, not really, because there are like billions of neutrons, I'm saying neutrinos, that are doing the same thing. So in terms of how dense it is, it's very dense, and that's the reason why in our local clusters, basically when you are talking about like Mercury, Venus, Earth, Mars, Jupiter, Saturn, is like everything is good, absolutely accurate. The moment we start to zoom out, then we start to know how does that happen. That happens after dilution. So it's everywhere. And okay, then we did the mathematics, like, okay, balance out the equation to figure out the missing mass, so to say. It's more than the normal mass. That's another aspect. Is like, okay, we thought, okay, some percent are missing. No, we are the some little percent. We are the like 5%, and that's the big 20%. It's like we knew the oxygen, we did not knew about the nitrogen in the atmosphere. So that's the interesting part. This dark matter, or the X variable, is much more than the normal material. Now it interacts with the gravity. That's the absolute part. We know it has effect on gravity. We can observe it, and we can even map it out. And I'm reasonably sure you type dark matter, you will see images like this. Now, what are these images? Like XY box dimensions, and you see some cloud structure in that. Is that we used Hubble telescope, and it started to observe, as in like we were always observing, we started to calculate for it the gravitational lensing effect. We start to see basically multiple time frames, photographs, multiple things. There are people whose job it is to construct it. So they constructed the detail, and we got the first detailed map of basically dark matter. And here's the map holds true. Basically every scientific effect that we can measure around it, it does hold. Like we know for a fact something is there. What, we do not know, but how much it's affecting, we know. We can observe that aspect. Basically it's a lens that you can't see the frame around, but you can see the effect of the lens itself. So it's a very known, and it does react with gravity, but it has a very weird properties. It does not react with itself. Now every matter, why the heck matter becomes into things? Because it collapses, it reacts with itself. Basically you have a dust cloud. Let's just say you have dust cloud. If few particles interacted with each other, they will create a gravity gradient. Gravity would become higher in that place, then more and more particles will start to pile on, and slowly and surely you will have, boom, a star. And then you will have other things colliding and becoming planets. This is normal, this is known, this is understood. But dark matter does not behave in that way. It does not react with itself. That's why you cannot just find the density in such a way that like, okay, there is this black hole, so density around the dark matter, density around the black hole would be highest. Why? Because it's like following the gravity. It's not doing anything like that. So interaction wise, it's not doing anything. It's like it's just there. Basically you can't interact with it, but it can interact with you. So that's the funny part. That's why scientists like calling this dark matter was a mistake. It does not follow the normal rules of matter. Dark simply means we do not know. Matter was quick done. But again, for scientists, people are like, yeah, it's just a poor naming convention. We'll improve it with something when we have final awesome things. So that was the dark matter side. We did the equation. We are like, okay, 20% and all that jazz. We got that idea. Now there is another problem started to become much more evident once we started to find, okay, there is an unknown. What other unknowns we are missing? Well, expanding universe started to become another apparent factor, because we know Big Bang. It's an absolute known thing. Because why? Because we observed the universe and it was expanding. So somebody thought, what if we start to rewind it? Let's say clock is showing tuk tuk tuk. What if we rewinded the clock mathematically, as in tuk 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 tuk? We got the Big Bang. Everything works out. Now again, we did the mathematics. We are like, okay, if Big Bang is true, we will observe this kind of thing. Like let's say microwave background radiation. This will be the pattern of it. We launched satellites. We tested it. everything works out. Other aspects of it, like we will see planets being formed, we will see stars being formed, we will see stars nurseries, more and more better telescopes we started to make, the better we started to understand it. Timelines start to get refined, where it went from like 15 billion to 12.7 billion. Like the time zone is getting more and more refined. The more telescopes will launch, the more fine tune will get there. So it's there, it's absolute, we know this, we got this, everything is fine and dandy. Now here's the current understanding at that time was that we had this boom, things expanded, but it will calm down. Why? Because again, the energy is not infinite. We are not seeing that energy right now. So that means the energy ran out at some point in time, and things started expanding. Now they are expanding on their own energy. Let's say call that inertia. Now here's the, in normal universe, what should have happened is like it's starting to expand and then it calms down. It's like, yeah, it reaches a low level energy state where it's like, okay, I'm a chill, I'm not going to do anything. Or then another mathematics was like, okay, let's say that once that energy runs out, it will collapse. Same way a star does. Like star is running on basically a very critical balance of gravity and fusion. Fusion is pushing things apart, gravity is collapsing things. Now it generally remains in a balance, but what happens if fusion runs out? It collapses. So that was the same logic we thought applies on a larger scale. It's like, everything is running on that energy, that initial big bang energy, things are expanding and they will collapse. That's why people were like, things supposed to collapse, because it makes sense. Like we observed this with stars and all that jazz, so like it makes sense, but that's not happening. So what happened, like then people are like fine-tuned. It's like, okay, it's supposed to like just go there and chill out. Then more and more observations started to occur. We started to observe what we call rate of expansion. Basically, what is the velocity, acceleration, so to say. We, instead of going for speed, we started to aim for acceleration. Is there any acceleration? It's supposed to be decelerating because the Big Bang happened quite a long ago, so it should be decelerating, but we did not. What we saw was acceleration. Basically, it was going from 500 kmph to 50,000 kmph to 5 million kmph. Like what the hell, how the heck it's accelerating, and it's constantly accelerating. Then we are like, okay, this is a very big thing, we have to need proof, we need absolute proof for that. So we started to look deeper into redshift. Now one thing I have to explain about redshift is like, redshift does not mean that you will see a galaxy which will become red. Redshift simply means the signature of every material is in the light pattern itself. That's why we have spectrum graph. Now spectrum graph can show you like, okay, this is a hydrogen spectrum graph, let's just go with that, and you will know there should be a big fat line in blue, there should be a big slim line in basically red and all that. There is a signature to it. It's like a chemical fingerprint. It cannot be tampered with. Like we know for a fact, it's absolute. I mean, like we predicted the atmospheric composition of other planets using this, and when we went there to check it, like in case of Mars, it was absolutely true. So this system works. It's not something like, oh, only applies on Earth. No, it's a universal thing. Now once we started to go into redshift, what does that mean? That signature would be there, the pattern, basically the ratio, the lines would be absolutely there, but they would have shifted to the red. It's like, it would not make sense. It's like, how the heck you can shift the pattern? Because the space between those 2 points expanded mid-transit. Basically, it's the photons that left that place, it was like, I'm going to y, and that y is like, let's say 1 light year away, but during its transit it was like, okay, now it's 10 light year by the time it reached there. So light shifted into red. Now another aspect of this can be also observed. Light can be blue shifted. Now like, why the heck something will blue shift? If you are in a path of a galaxy that is colliding to you, like say in our case Milky Way and Andromeda, they're colliding, so in those scenarios we'll start to observe this blue shift. Hey bro, this star, let's say this red dwarf, supposed to have signature like this. We'll observe other signatures like that. We'll do the mathematics like where the signature should be, and they're like, okay, how much it has shifted. Based on that, we can figure it out how quickly it's coming towards us. So it's a known thing, absolute. More and more equipments were used. We went from using negative to actual CCD to like, very cooled, super cooled apps, superconductor level CMOS systems and all that jazz. More and more evidence started to pile up. It's like, dude, it is accelerating. Like somehow there is this energy that is pushing things apart, and it's doing a much and much higher pace. It's like it's going from 1 megawatt, 1 million megawatt, 1 trillion gigawatt. It's like it's expanding. So we had no clue what kind of thing that has this kind of level of energy, because we thought Big Bang was a big deal. This puppy is like, bro, hold my beer. So that's the whole point. We have a proof, we have observed it, it's absolute, but what cost it? So that's the whole point. That's what is we talk about when we are talking about dark energy and dark matter. We observe these things, we observe the effects of it. It is absolute, it's known, we got this, we know this. It's just what exactly it is. Like we know the radiation. Let's say there is a rock, it is radioactive. You do not need to know what exact spectrum of radiation it has. If it starts to end people's life around it, you're like, yeah, I got this, I don't need to test that. So That's okay for some things like engineering and all that, but not good for scientific investigation. But in scientific investigation, we started to use mathematics. It's like, okay, we know for our fact that whenever we try to simulate basically galaxies born in our supercomputers, the output was always gibberish. It was never looking how it's supposed to look. Then somebody came up with a brilliant idea. Hey, why not, we are thinking about like dark matter and dark energy, let's feed that into the equation. It's like, x supposed to be this much, y should be this much, and then fine tune these values until we get the basically projected model that matches our reality. Basically, we have some mathematics, we have to find unknown, we have the final product. Let's fine tune these two variables. So that fine tune variable we have, it's like luminous material, which basically starts glowing things, is 0.04%. Then we have non-luminous matter, basically dust cloud, planets and all that, that is around 3.6%. And then we have dark matter. Now this dark matter is 23%. Then we have energy that is expanding it, that is giving the universe its structure. So like expanding a structure, not a constant structure. That is from dark matter. The expanding structure is coming from dark energy. That dark energy is supposed to be 73%. So it's not absolute. Right now we are not in a position where like this is absolute. So you will always see people say we know about 5%. Then there is 20 to 28% of dark matter. Then there is 65 to 70% of dark energy, depending on which computational model you are looking for. So we figured out the distribution of it. It's basically fancy mathematics where it's like, okay, if x is this, y should be this much. We did this mathematics. Now this is where I have to introduce a caution. Basically, I would urge people to relax. Just relax. Now this is one thing I have seen many comments and throughout the world. It's not that only this one and that there. No, throughout the world I have noticed people making the mistake. It's like people think themselves very smart when they say things like it's beyond science. No, science is not man-made. It has nothing to do with human. When you go somewhere, let's say you have a notebook, you go somewhere and you note down something, does that mean the content of that notebook is made by you? No, you observe something. So similar happens here. Science is not man-made, it's man-discovered. Basically, we discover Mount Everest. We do not make Mount Everest. So what does that mean? That simply means the science, the tools, the logic algorithm that we built was designed from day one to figure out unknowns. I'll give you a simple example. Let's say you are a dude who's like, okay, we are inspired by Newton. Is like, hey, I'm gonna send a light through to a prism and we're gonna have color spectrum. It's like everything is awesome, no problem. You are like, hey, what if I want to figure out the temperature of the color? You're like, okay, I'll put thermometers there. Awesome, things works. But here's the deal: all the color temperatures, they are like, okay, but here's the one that is on top of red somehow gets hotter than that, but you cannot see what's causing that. That was infrared. That's how we discovered infrared. We know from day one that we are like a more of like we're trying to solve a mystery. We can observe the effect. We try to double check it, triple check it. When we are absolutely sure, okay, something is there, then we try to deduce it, like what the heck it is actually there. So that's the whole point. That's science. That's basic point. So calling something that is beyond science is meaningless. Basically, you can say, if you really want to be like, very anti-human and be like, yeah, our current scientists have not figured it out. No problem, because you have to understand that in our history, you can go like right now at this moment in time, 2020, you can ask a child, let's say class 5 or 6 or even 10, and they will tell you like how the heck rainwater works, like where the water comes from and all that jazz. Go to few thousand years ago, nobody would tell. Heck, go few hundred years ago, people would not have a thorough understanding of water cycles and all that jazz, how season was and all that. Like those things were unknown. We figured it out using the tools of science. Same way we will figure this out. Maybe in 5 years, maybe in 500 years. That's not an issue. We will figure it out. And what we are seeing right now, at this moment in time, we are seeing a birth of new scientific field. So this is kind of different because around let's say after 1950 we did not made any new science. All we did basically from 1950 to 2020 we improved things like crazy. Like our efficiency wise, basically how much we can do with 1 watt of electricity, that went ludicrous. Like 1 watt of electricity in your mobile phone can do what hundreds of supercomputer could not do in 1950s. So reality is like we became very inferior, but in terms of science, no new science has been introduced. This time you are seeing that. You are seeing how science is made. Basically, okay, we deduce that this is not black hole, that is rejected. Okay, this is not concentrated, this is very dilute. Okay, we can remove that. Like brick by brick, you are seeing the directions that lead us to a final product. And we are building tools. You can see what are the thought process that people utilize in order to build the tools that allow us to see the unknown. Same way I specified, prism was used to figure out there is infrared. Here we are building giant chambers filled with a absolutely crystal clear pure water. So there will be xenon there in a chamber or mixed with the water, and it will react with something. Why it will react with something? Because our current assumption is that dark matter is basically a type of matter which is not reacting normally. It's like it's a matter, it's not reacting. Like how the heck that makes sense? That makes sense in our current particle models, whereas the particle physics model, we have neutrinos that behave almost the same way, but neutrinos are very dense. Like once we started to figure out how to detect it, it's like yeah, it's everywhere. So we are thinking the same logic. It's like, okay, we detect a neutron. What if we make something that is even more sensitive? Then it may allow us to detect what we call WIMP particles, weakly interactive particles, and all that jazz. So there are tools being built right now, and some tools are already active. They have not yielded result, but again, that's how it takes. Like it's not something. There's supposed to be dark matter. 5 minutes later, this is what dark matter is. It takes time. You are seeing a birth of a new scientific field at this point in time. So we are kind of very lucky, because once we solve this out, we'll have very clear picture from the beginning of Big Bang to this point in time. Like because we understood Big Bang, like it happened, it's absolute. So we are seeing a train, but we, in terms of detail wise, we did not have, because we could not figure out how the heck galaxy formed. Mathematics was missing some variables, so to say. So that's why I would urge you to relax. So this was my presentation on dark energy and dark matter. I hope you liked it, learn from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me extra disappointment, and please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.